You're welcome to Maths 203. We're now in the topic Fundamental Laws of Integers, and this is the first part of it. My name again is Dr. Lois Adewoye Ademola. So in this chapter 5, we'll start basically with what we call the Peano's postulate, first and second principle of mathematical induction. We'll consider a lemma. We'll find out what primes are, what coprimes mean, division, algorithm, what it's all about, what the GCD, the greatest common divisor, what is Euclid algorithm, and we'll consider an example. What then is the Peano's postulate? Basically, it states that 1 is a natural number. 2, every natural number n has a unique successor n plus 1, which is again a natural number. It also states that 1 is a unique non-successor of the set of natural numbers is counting numbers. Okay, 1 is a unique non-successor. And the fourth one says that distinct numbers have distinct successors. Okay, and satisfying this condition you see on the screen. And the fifth is that it satisfies the principle of induction, meaning that if you have S, a subset of the set of a natural number, this is B, not just B, such that 1 lies in S and you have n plus 1 in S, whenever you have n in S, then S must be equal to the set of natural numbers. So if you have a subset of the set of counting numbers n, and you have 1 in it, in that subset, and n plus 1 is in that set, I haven't seen that n is already in it, then definitely S is equal to the set of natural numbers. So that is what the Peano's postulate states, and you should be able to state all of these 5 points, okay? All 5 of them. You should be able to state them, okay? Next is what we call the first and second principle of mathematical induction. You are expected to be able to state them, not necessarily prove them. I just need you to be able to state them. Okay, so you should be able to state that the first principle of mathematical induction states what, as you see on the screen, everything here. By now you know mathematical induction, the first one, because you did it in Maths 103, I think. You must have done that already there. Sorry, 101, that was when you did mathematical induction. And now we are adding another to it, which is the second principle of mathematical induction. And this one states something different. In the case of first principle, you check the statement P1, you check the statement, you assume the statement PK, and you prove PK plus 1. But in the second principle of mathematical induction, this one says you have P1, so the statement P1 holds. Then PM holds whenever PK holds. For all K is less than M, then Pn holds. Okay, so there's a unique difference. Here we have PK plus 1. Here we just check for PM whenever PK holds. Okay, so the two unique differences. You should be able to note the two differences and be able to state them. Now we have a lemma before us. The lemma is called the well-ordered principle of natural numbers. So I'm supposed to have emboldened this, so I want to align it for you. So if I say, state the well-ordered principle of natural numbers and prove it, all I want you to be able to do is say this: every non-empty subset S of natural numbers contains a first element. That's all. That is what you say when you're stating it. So if you're asked, state and prove the well-ordering principle of natural numbers. So this is the well-ordering principle of natural numbers. It simply states that every non-empty subset S of the set of natural numbers contains a first element. And this is the proof. The proof is such that we prove that S contains no first element, meaning we're proving by contradiction. So we'll assume that there's no first element in that our subset S and see if we get a contradiction. So to do that, we'd first define a set. This set will be the one collecting everything that shouldn't be in S. It is defined such that Y is a set is an element in the set of natural numbers, and Y is less than X for every X in the set S. Remember I said this set T will be collecting everything that shouldn't be in the set S. So we don't want one in the set S because we said it doesn't have the first element. That is what we're doing. We're proving by contradiction. So we define it, the set, this way. So we define it in such a way that this set T collects everything that shouldn't be in S. It shouldn't have a first element. That's our target. So let's see what happens. So define T to be this set. Then clearly 1 must be in T. Because if it is not in T, it will be the first element of S. So that's it. We know where 1 is now. Now suppose that for some natural number K, such that 1 is less than or equal to K, we have that K lies in T. So now every K, basically we're proving by induction. If you note, I've checked for 1 and now checking for K. So we want K to be in T, because if K is not in T, it definitely will be in S. Is that not so? So T such that then K must be less than X for all X in S. Is that true? Because that was the condition for our definition of T. K will be here now, and it will be less than X for all X in S. Also, we cannot have K in S, just like I said. For if so, K will be the first element in S, so it cannot be. It just has to be in T. Thus, K is not an element of S. And every X in S such that K is less than X, or K plus 1 is less than X. That is, I have checked for 1, I've seen that K cannot be in S, then truly, if I go by induction, then everything of this form must not be in S. Do you agree to that? It must be in T. So we expect that to be in T. So everything here, because that's what T does, it collects all the elements. So this must be in the set T. Okay? Hence, K plus 1 lies in T. So by the principle of induction for Peano's postulate, do you remember? Let's go back and see. For Peano's postulate, what did we say? Look at it here. I said the principle of induction, the fifth identity. It says that. Clean it here. Once you have 1 in the set, you have n plus 1 in the set. For whenever n is in the set, then that set must be equal to the set of natural numbers. Do you agree now? Okay, so let's go back now. So our set now is T. It's T that collected everything, remember? Everything is in T. And based on what we just learned, we learned that this must be equal to the set of natural numbers. Hey, what do you think about this? I have not concluded this my proof. If T is equal to the set of natural numbers, and we already know, okay, let me complete the proof. Maybe I put it in the next part of this proof, but let's go on. But we all know that T is a subset of S because everything is smaller than S. And now we know that T is actually equal to the set of N. If N definitely, and S we know is a subset of the set of natural numbers. This is not a contradiction. T cannot be bigger than S. Is that not so? So clearly this is a contradiction. We got a contradiction, and that ends our proof. Okay? Again, I'll take that ending again. Let me take it again. So now we've succeeded in showing that that set that collects everything that should not be in S is now equal to the set of natural numbers. But we know that T is a subset of S. S, which is also a subset of what? The set of natural numbers. Can T be bigger than S? If that is the case, clearly it is not true. So we have a contradiction. So that's the proof. Okay? So you can write it in words so that it's clear for you too. Okay. The next things you need to know are more definitions. So if you have A and B in the set of integers, we say A divides B. We write it simply as A with a straight slash, not by like this, not like this, okay, not that way, and not like this, okay. These two mean something else, especially for us in loop theory, okay. So we say A divides B to indicate that B is divisible by A. Okay, for instance, 2 divides 8. Is that true? So 8 is divisible by 2. Okay, so what then is a prime number? If you're asked what a prime number is, a prime number is an integer p. So we always use small letter p for prime numbers, not capital. Okay, it's an integer p greater than 1 whose only positive factors are p and 1, not n, but and 1, p and 1. Okay, then we have a prime number. I'm sure you know that already, but you need to know the definition and be able to state it. Okay, now the greatest common divisor, GCD, is the largest positive integer d, which divides both a and b. So we write the GCD of a comma b is equal to d. E.g., if you have 10 and 25, what do you think is the greatest common divisor of both of them? Definitely 5. Okay, both of them, the greatest common divisor. So that's an example. Now, two integers a and b are said to be coprime. So I could ask you to define the word coprime. If there is no integer other than -1 or 1 dividing both a and b. Okay, so we write GCD of a and b equal to 1, or GCD, or simply ab equal to 1. For example, 6 and 23, there's nothing common to them but 1, so we say they are what? Coprime. That is 6 and 23 are coprime. Okay, that's how you define coprime, and that's an example of coprime. Now we have an example. Or before we talk about the example, let's look at this illustration. Given any two integers, so this is talking about the division algorithm, which brings us to an example shortly. Okay, so we're talking about division algorithm. Given any two integers, a and b greater than 0, we can find unique q and r such that you can write a as b times q plus r, and r is often less and always less than b, and it could also be 0. Okay, for example, if a were to be 125 and b were to be 10, you see that if I take 125 and divide by 10, how many times would 10 go into 125? Definitely you will say it will go 10 and 12 times. And what will be your remainder? The remainder will be 5. Is that true? So it means I can write, so based on what we've just done, that we clean a space for us up on the screen. I can write 125 to be equal to 10 times 12, 10 times 12 plus the remainder 5. Is that true? Because this is the same as 120 plus 5, and this are the same. Okay, that's just what the division algorithm, the main part of it starts with the concept, oh, if I divide by something, it will go a certain number of times, and then I'll get a remainder. And then, so in a general way, it states that if I have a, b, I can find q and r such that a can be written as this, r less between 0 and b. Okay, so because it's an example. So for more on the Euclid algorithm, at this point, I need you all to check your lecture notes. By now, you must have gotten the lecture notes. And if you haven't, I have been telling you during the class, get your lecture notes, okay? Okay, now, theorem 1. I tagged it theorem, a very key theorem because you're going to be using it, okay? So given any two integers a and b, if h is equal to ab, meaning that the GCD of a and b is h, then there exist integers s and t such that h can be written as the sum of s times a plus t times b, which is what you see there. So this is a theorem. You should be able to state it. Whenever I have two integers and my GCD of the two integers is h, then I can find integers s and t such that h can be written in the form you see that I've circled on the screen there. Okay? So I tagged it in this video, theorem 1, but I think it's called a different label on your lecture notes. So, but that's because I need to call it in a lemma shortly. Okay, so we have a lemma, which we're going to prove, which is all continuation of the division algorithm. And that lemma says that given any two integers a and b, there exist integers s and t such that this sum is equal to 1 if and only if a and b are co-prime. When do we say something is co-prime? We say it is co-prime if a comma b is equal to 1. Is that not what we said? If you check your definition, you can rewind the video to see that. So now we want to show that once we have two integers a and b, then s and t will take this form. Take the form. You can write it in this way. But recall that our theorem, we had said that once you have two integers, so the lemma is actually an offshoot of the theorem. Okay, so if you have two integers a and b and h is the GCD, then you can write h in this form. You can find s and t such as exercise that form. Okay, so we want to prove this lemma. Now we have two integers a and b. We're saying we can find s and t such that this is so on the grounds if and only if. So it's a two-way proof, more like I'm using this arrows, if you remember your logic. If and only if a and b are co-prime. So is either I accept that a and b are co-prime and show that this will hold, or I accept that this holds and show that a and b are co-prime. So let's see how we started in this proof here. So in the proof in your video here, we started by accepting that this is true. So we say let this sum be equal to 1. Then for this to be 1, if you're going to add two things together, so if I happen to want to add, say, x plus y, and I want it to be 1, clearly this has to be smaller than this, is that not so? As in x has to be smaller than y. Anyhow, one of them has to be smaller, because if I happen to have taken 5 plus 9, it cannot be equal to 1. So you have to be careful and select our values in such a way that the sum of these two items would give us 1. So let's see. I have to pick x to be less than 1, smaller than 1, and I have to pick y to be less than 1. Is that true? For this to be equal to 1. You could get 0.1, 0.1. Let's check it again. So we just need values small. My screen is disappearing. So I will need maybe 0.1 plus 0.9. Definitely I'll get 1 this way. Or some other values, okay? But definitely x and y will be less than 1. So in that case, if we compare it with what we're trying to sum here, we have SA plus TB. Means my SA must be less than 1 and my TB must be less than 1. Meaning that A and B must divide SA plus TB. Okay, that's sum. They should be able to divide because they're less than. So A and B must be plus or minus 1. Is that not so? Because it has to be smaller than 1. And so, definitely the GCD of A and B will be equal to 1 based on the argument you have seen me use thus far. Good. Conversely, so we've succeeded in showing that it's co-prime, because if I have this, it means I've shown that it's co-prime. So the converse way now is to accept that it is co-prime and show this will take place. Okay, so let's see how that goes. We've seen the first part, basically using the fact that the sum, for it to be equal to 1, both terms must be smaller than 1, and if they are smaller than 1, definitely A and B must be terms either positive 1 or negative 1, and they will divide the sum. And if that is the case, we get the GCD to be equal to 1, meaning that they are co-prime. So the converse is what we want to prove now. So if A and B are co-prime, meaning that this holds, then definitely by the theorem, I know I have A, I have B, and I now know my H to be equal to AB, and my H in this case is 1. What does that theorem tell you? It tells me that SA plus TB is equal to H. In my own case, H is 1. So by that theorem, the proof is complete. And that's all to the proof. Okay, so the second part follows from the theorem we saw the other time, which I said you should be able to state by a theorem that states that if I have two integers A and B such that the GCD is equal to H, then the sum they exist S and T such that this sum equal to H. And in this case, because we know that GCD is equal to 1 because it is co-prime, it means this is true for the lemma. Okay. And now we go to, most students like this part of Euclid. Most computer science students love it mostly because they use it more in most of their works. Okay, so we have a question before us here. It says we should find the GCD of A equals to 3 to 3 and B equal to 1 to 4. And we're to use Euclid's algorithm. And after finding the GCD, meaning that we should find H of 3 to 3 and 1 to 4. It says after finding H, you should also prove that you can find this SA plus TB. We know our A already. A is 23 to 3 and B is 1 to 4. So we're to find this. That's a lot of work before us, but let's learn it first. Practice makes perfect. By the time you know what to do, it'll be easy to work with. Okay, so we need to find GCD first. So how do we find the GCD? Basically, you're working backwards. You're going to do this. You know your A, you know your B. If I take 3 to 3 and divide it by 1 to 4. So you need your calculators now. How many times will it go? It'll go 2 times. And your remainder is 75. You can confirm. Meaning that I can write this as 3 to 3 is equal to 2 times 1 to 4 plus my remainder 75, which is what we did earlier. Do you remember? Now, that's what I've done here. This is the first step here. I was able to write it. That's what you see here. Now, my bracket, I didn't use a bracket here. I used times for this step here. And this is how I got it, which is what I did right here with the remainder. Okay? Now, that's my first step, because that's what the Euclid's algorithm does. If you check the notes, you will see it has to find Q1, Q2, R1, R2, and all. It keeps going till it finds all the values. Okay, so now I haven't found that. Not this. My interest is in this number here. I bring it forward here. And my remainder, I bring it this way. Now, see what I'm going to do. This number, 1 to 4, I'll take it again and divide it by my previous remainder, 75. How many times does it go? It will go one time, remainder 49, which means I can write 124 as 1 times 75 plus 49 is what you see right here. And this is how I did it, which is what I'm showing you here. Again, so I haven't gotten this. I have to keep repeating my my recurring equations or solution sums until my remainder is 0. So what I have to do now, I take my 75, bring it forward, and take 49 and bring it forward. 49 is my latest remainder, remember? So I take 75 again and divide it by 49. How many times does it go? It'll go 1 time. What's your remainder? The remainder is 26. You see that? Again, I can write 75 as what you see here. As 75 times 1 plus 49 plus the remainder 26. You see it? Okay. I haven't done that again. My remainder is not yet 0, is it? So I keep going. I take the process again. My 49 comes forward here and 26 comes forward here. How? I take 49 divided by 26. How many times does 26 go into 49? It'll go 1 time. Remainder what? Remainder 23. Meaning that I can write 49 as what you see right here. I keep taking the process over and over again, divide, get my remainder, and I kept doing that until I got to this stage here. By the time I took 2 forward and 1 forward, I saw that 2 was just 2 into 1, or 1 times 2, which is what I have here. No remainder. No remainder, because 2 divided by 1 is just 2. No remainder. So since there's no remainder, I can find my GCD. So what's my GCD? My GCD was the last remainder I obtained before I got to this stage I was. What was the last remainder? It is this one here. So GCD of this value, which I started with from up here, this 2, which is what you see here, is 1. So we finished solving the first part. We're told to find the GCD using the Euclid's algorithm. So that's just the first part. We're here to do the second part. So the first part is as you've seen. You can rewind the video, play it. If I'm too fast, I'm told there's an app. Okay, I know there's an app that makes you talk slowly. You can do slow motion then. But this is how you go about it. Now we want to find how to express it in SA plus TB. But to do that, I will need you to note something, which is what you see on the screen now. Now, recall from our previous screen, clean this. Before we got the GCD, we got this array of equations, this one here. What you see here, you see? So what you have. This is what I have copied and pasted here. See it here, all of here. Okay, the same thing. But what I've done now is to walk upwards. How? Watch. Making 1 my remainder here, subject of the formula, I'll get 3 minus 1 into 2. Can you see here? See it? Now I have highlighted the ones that I kept bringing forward. All those that I kept bringing forward. Can you see them? I highlighted them. All these ones. I didn't highlight this ones here. I did not. Note that. So you will see why I didn't highlight them. So you will see us use them carefully. Okay, so I made the remainder subject of the formula. And so I have this. Make the remainder here next subject of formula. What you get? You get this, because 23, this will go forward. This term here will go forward. and then you get this. Is that not so? I have carefully put the ones highlighted in brackets, not carefully because I don't want you to touch them later. You see, they're carefully in brackets. Put them carefully in brackets, okay? I made this also subject formula. I did same for each one of them till I got to this one, making them subject of the formula, working backwards. You see that? So I want you to carefully note that and remember to do that because that's what you will be working with. So you keep this aside and we would use it shortly. Our target again is to find the sum for SATB. We know the GCD is 1, so we're working backwards. Okay, so now on the screen, the first step, working backwards, so I have taken a snapshot, I snipped this out for you, this screen, we're working backwards. We're moving from down here, going up, okay, I'm going up carefully and slowly. So the first step for you to do is to bring out this, making 1 the main remainder. So you can see 1 is now here, it's a target. So 1, the same thing you have here, that's here, okay? So I've made this with a formula. Now, the next step, your step 2, you might have more than 2 steps, depending on the question you're solving. This 2 in the bracket, like I said, I don't want you multiplying it, I don't want you touching it, I just need you substituting it. Remember, it's the previous remainder, and it's here, look at it here. So wherever I see 2, I'm going to drop this value here. That's 23 minus. So in place of 2, can you see the 23 minus 7 times 3? You see it there? The same thing. Okay? So we substituted for the remainder 2. Now watch how I multiply out. I didn't do 7 times 3 and put the big value for it. No, I left it as it is. Okay? You know why? I'm going to bring all the numbers that are 3 together that are looking like these are remainders. Any number that is exactly the same ones, just use them. Now there's a 3 here and I have 7 3s here. So I carefully bring it down. I want to open the bracket, that's why, because there's a minus sign out here. It's the minus here. So 3 remains 3. I want us to carefully follow it. There's a 3 here, and then there's a 3 here. There's a minus sign outside this bracket here. If you note, there's a square bracket, so let's be careful there. Okay. So the minus 1 times 23 is minus times 23. Minus 1 times 3. You see there? I didn't open the bracket. Note carefully, I didn't. I left it 23, but just put the minus 1 beside it. Minus times minus plus. 1 times 7, 7. I didn't open the bracket, I still kept the 3. Okay, so you have to be carefully watching what you're doing. Now, there's 1 3 here, and there are 7 3s here, meaning that if I have 1 apple, and I have 7 apples, how many apples in all? There are 8 apples. Okay, there's 1 3 here, 7 3 here. That's why you have 8 3s here. That's how I got the 8 apples. My minus 1 20 times 23 stays as it is. Okay, you've seen that? So how many remainders have we substituted? We've done the very first one, which was already there. And then we move to the next step, which is this one here. And now we're at this point here. We're there. We're at the... So like I was saying, we started here. We moved here. Now we are here. Right at this point. We're substituting anything where we see 3. So you understood how we got here? So now the next step is to substitute 3, because 3 is the next remainder. Sit here. And the value for 3 is 26 minus 1 into 23. So wherever I see 3, the value 3, not 23 but 3, I'm putting 26 minus 1 times 23. So you can see it in a bracket. Carefully kept there. All I'm going to do, my 1 out here keeps following. Have you noticed? It just keeps following because that's my GCD. It just follows carefully. Nobody tampers with it. It obeys, obediently follows. So back to substituting 3. So 3 is this. So I bring in the 8. I don't expand out totally. I just make the 8 attach itself to the number 26. Are you seeing that? 8 times minus 1 is minus 8. You see that? And then there's 23 there. And my minus 1 times 23 is still there. So let's look carefully now. I didn't open the bracket. I didn't touch these numbers out here. Remember that? I was more concerned with carefully. Sorry. I mean, I only made use of numbers. Oh, there. Let me not get you confused again. I was saying I didn't touch this ones here. These ones are highlighted. But I could play with these ones. These ones can multiply each other, talk to each other. Have you noticed that? But the ones that are highlighted, I didn't touch them. They just kept following carefully. I only substitute for them whenever I got to the next remainder. Okay, so back to here now. We've opened the bracket carefully without touching those ones that we shouldn't touch. And we have what we have on the screen. So now, how do we simplify this? Same way. I have 826. There's no other 26. So I just have 826. Now I'm owing 823 and I'm owing 123. More like I am owing 8 naira and I'm owing 1 naira. How many nairas am I owing? I will be owing 9 naira. Is that not so? That's why there's a minus 9. Okay, so that's how we got that value there. So you have minus 9 there. See that? So that's how we got to this stage here. So we've succeeded in substituting remainders up to right here. We finish this. Now we have to substitute for 23. So let's see how we do the next one. So we're substituting for 23. That's where we are now. So 23 again, we've done here, we've done here, we've done here, we're right here. So 23 is 49 minus 1. 49 minus 1 times 26. So you substitute carefully wherever you see 23, which is right here. You can see my new value of 23 with the bracket. Again, 8 comes forward. My 1 obediently follows. Remember, it's a GCD. It just follows carefully. It doesn't go anywhere. It just obeys. Okay, 8 times 26 stays there. Minus 9 there and the bracket with our value for 23. Minus 9 goes into the bracket. You have that. You have this. Minus times minus is plus. 9 times 1 is 9. And the 26 obediently follows. Again, like we did before, I have 826 right here. And I have 926. How many 26 in all? 1726. And I owe 949s. Okay, so that's how we got what you see on the screen, the next step there. Okay, so we're here. We can't do anything more but to check for the next remainder for substitution, which is next. We've done this. We're right here now. Going up, remember? We're going up. So now we're at 26. 26 is 75 minus 1 times 49. So wherever I see 26, this is 26. So where's 26? It's right here. Its value is substituted. And minus 9 times 49 obediently follows too. Again, just like we did it before. Now 17 will multiply 75. Minus times plus, that's why there's a minus there. And the 17 times 1 is still 17 and 49. And then this one follows obediently. I have 17, 70, 75s. Are there other 75s? No, only the 17 of them. So keep it there. I am owing 1749s and I'm owing 949s. How many am I owing in all? I'm owing 2649s. So that's how we got to the stage you're seeing here now. Okay, so we've succeeded in simplifying as far as we can. And we've finished with here. We're now going to substitute the next remainder, which is the next remainder. The next remainder is 49. So we're at 49. Let's go. So we're substituting 49. We've moved all the way to right here. I think we're almost there. because we're going to substitute 49. So substituting 49 is 124 minus 1 times 75, which is what you see here. You can check and confirm. And so 17 times 75 follows obediently, still follows. Minus 26 goes in, and it will be minus 26 times 124. Minus times minus is plus. 26 times 1 is 26, and then we have 75. Again, just like we did before, we find out those that are common. I have 17 75, I have 26 75s here. So how many in all? I have 43 75. And the minus 26 of 124 follows us obediently too. So we're at this stage. So we can't do more than that. We have to go forward. So we go to the next stage, which is the very last step, and that is substituting 75. And this is the value for 75. So substituting that, where's 75? Right here, we substituted. This is 75, 43 follows. Remember, 1 just keeps following obediently. Okay, it's the GCD. So again, we substitute 75, and this is 75. The minus 26 follows. We open the bracket carefully, and we have for 3 times 2, and we have minus 86, and we have that, and this comes down. So we collect like terms again. I have 43, 3, 2, 3, so that's okay. I am owing 86 124s, and I'm owing 26 124s. How many in all? I'm owing 112 124s. Wow. You know what this is? This is A. Right here is A. This is B. Right here is B. It means I found my S and I found my T. So this is same. Basically, this is equal to 1, remember? So I just rewrote it like this. So we found S to be 43, and we found T to be 1. Minus 1, 1, 2. That's 112 minus 112. Just like my S. This is my T, and this is A, and there is B here. That's plus. You know B is going to, so T is minus 112, and S is 43. Okay, so thank you. This is where we'll stop with this part of chapter 5. There's a second part of it, like I said in class, that will come towards the very end. Please practice against Monday by God's grace. Thank you. Or against our next class. Thank you.